next contribution is a keynote lecture, and we're honored here today to have Professor Mike Janik as our keynote speaker today. Professor Janik is at Penn State University, and he's been working for a number of years on using computational methods to understand electrochemical systems, and thermochemical systems is related to energy conversion and storage. I've known Mike for a few years, and he's also a lead on one of our NSF-funded joint proposals, DEMREF. He leads the computational effort there. In addition to his contributions in theoretical electrocatalysis, Mike is also an excellent runner. And I found out when we were together at a retreat in Florida, I ran with him, and I realized how slow I was. So when the race was happening a few days ago, I didn't even dare to run because I knew I was going to lose. And of course, Mike ended up winning first place, so in addition to his catalysis. But today he's going to talk about density functional theory is related to electrocatalysis, the effect of pH in cations in hydrogen oxidation reaction.
Thank you, Randy. Maybe 35 minutes on running would be more exciting, but I can't stand up here because my nervous energy will lead me to walk off the podium, so I hope everybody's okay with me down here. Thanks for the chance to talk to you, and especially thank you to the organizers of the conference for the chance to give this keynote lecture. I'm going to tell you about how we use DFT to study electrocatalysis, and I'm going to use as an example trying to understand how pH in the presence of cations when we move from an acid to an alkaline environment affects hydrogen oxidation. For the use in fuel cells, understanding hydrogen oxidation catalysis, moving to an alkaline fuel cell where we would like to then ideally get away from platinum, but everything I talk about today will be trying to understand platinum. But I do want to use this as an example to talk about how we use DFT to study electrocatalysis. We use DFT essentially for two purposes in catalysis, either to explain an experiment or to predictively design, because of course using first principles methods we can tell you something about a material that hasn't been studied yet. When we're trying to explain an experiment, we might start with an observation. So here we have experimental current density for the hydrogen evolution reaction. It would look similar if I showed you the hydrogen oxidation reaction, where we see Sabatier principle tells us the optimal catalyst is going to have some intermediate binding of some key intermediate hydrogen. So we have a metal hydrogen binding energy here. And we can explain this, of course, with a mechanistic picture of something that binds hydrogen too weakly. It's going to have a large activation barrier for the initial step of getting hydrogen on the surface. Something that binds hydrogen too strongly, so say tungsten over here, is going to have a high activation barrier or a slow rate of getting hydrogen off the surface. And our best catalyst, platinum, is near the top of this volcano because it has the right intermediate binding energy of hydrogen. And we use DFT to explain this. Of course, the Norskov group has done this very well for hydrogen oxidation, where we can use the hydrogen binding energy and try and predict a better catalyst and develop a volcano relationship, and then use DFT to probe alloys and such to find better catalysts. And of course, we do this in any catalyst design procedure. We do detailed studies to understand how the reaction environment affects our key variables. We determine what those key variables are, the hydrogen binding energy, and then we evaluate over some design space the composition of a metal alloy. However, this is difficult in electrocatalysis because the electrocatalytic environment affects these reaction steps. And as I'm going to show you, there's a big difference in the activity of the same metal atom when we go from acid to base for hydrogen oxidation. So here is results from Yang-Chao Horn's group, where we have the same overpotential, so the same voltage on an RHE scale, and we measure the current in a PMFC, an acid environment, or in a base environment, and we see a 2-order of magnitude shift in the current on the same platinum catalyst, suggesting that not just the metal, but of course the reaction environment is affecting the catalysis. And this result from Yushan Yan's group has essentially shown that this is continuous. So this isn't just going from pH 0 to pH 14, but we see a continuous effect of pH on the hydrogen oxidation reaction. So in order to use DFT to tell us something about this, we have to consider this complex electrocatalytic environment. And of course it's complex because we have metal particles on supports. Well, we're comfortable with DFT, taking that particle, making it a single crystal surface, and hoping we can ignore the support effect. We do that often in DFT. But we also have to deal with salvation here. The fact that we have an electrolyte, we'll have an aqueous electrolyte in the systems we're interested in, and we have to wonder how that salvation is going to affect the stability of intermediates, reactants, and products at the surface. And we have to worry about the electrochemical nature of this interface. It's electrified. The metal may be charged, and that's going to affect the rate. We also have the challenge of having to incorporate ions as reactants and products, and solvated ions, which are hard for us to handle with DFT. And we have electrons that are reactants and products, and we have to worry about, of course, both the rate of their movement as well as their chemical potential and how that changes as we change the charge or the voltage of the metal surface. So we have to develop DFT approaches to modeling these complexities. And it all comes down to calculating equilibrium constants and activation barriers, right? If we know the equilibrium constants for all the elementary steps, and we know the activation barriers for all the elementary steps, then we can tell you or predict what is going to be the rate of the reaction. But these equilibrium constants and rate constants depend on this voltage of our electron. So if we're absorbing, say, a cation, this could be a proton, absorbing to the surface, the energy of this electron, its chemical potential, or the voltage, is going to affect the tendency to absorb that cation. And of course, if that cation is a spectator species that may be a poison or may promote and some way alter the surface, we might wonder how the alkali cations, the potassium in that KOH solution, is going to interact and possibly affect our chemistry. So we need to know the equilibrium constants and how they vary the voltage. Now, of course, electrocatalytic mechanisms couple many steps. For instance, in the hydrogen oxidation reaction, we had hydrogen dissociation. There was no electron in that reaction. But then we had hydrogen desorption, and that had an electron. So if we couple electrocatalytic or electrochemical and just typical catalytic steps, then we worry about which steps might be rate limiting and how that changes with voltage. Because if there's an electrochemical step, if an electron is involved, then that rate constant varies with voltage. And of course, again, all of that's affected by the presence of the solvent and the electrification of the interface. And we want DFT approaches to be able to handle these complexities. So I'm going to do this across essentially 3 sections. This is the outline of the results part of my talk. I'm going to start not looking at the hydrogen oxidation reaction, but just looking at hydrogen and hydroxide absorption and desorption. And I'm going to try to understand how pH, or the presence of alkali cations, the presence of cations now in my electrolyte, because I'm in an alkaline environment, is going to alter hydrogen adsorption, desorption, and hydroxide absorption, desorption. Once I do that, I'm going to tell you what that implies for the hydrogen oxidation reaction. So how learning what we learned from surface science of looking at single crystal platinum electrodes and how the reaction environment affects absorption, desorption tells us something about hydrogen oxidation. I will have to get a bit empirical there. I can't say that we've finished all of our barriers and all of our microkinetic modeling of hydrogen oxidation in these various conditions, but I will tell you that we can tell you a bit more about how hydroxide and cations are important to hydrogen oxidation, explaining why the reaction rate changes between acid and base. Because I don't have barriers yet for the hydrogen oxidation reaction, I did want to show you that we can use DFT to calculate electrochemical barriers. I am going to show you how the presence of the cation affected CO reduction. And that's just going to be one slide at the end of my talk. So let's start with the hydrogen and hydroxide absorption, desorption. So here's a cyclic voltammogram. You can ignore the fact that there's 2 different electrolytes there. The peaks look pretty similar. Of course, when we call this the hydrogen region, we call it the hydrogen region because when we sweep the electrode positive, we say that hydrogen that was on the surface is going to now desorb as the electrode becomes more positive and the electron becomes more stable in our electrode. The proton goes off in solution, leaving an electron behind, and we see an oxidative current. When we reverse the process, of course, we see exactly the reverse process happen where the proton comes back on the surface. And these peaks line up in the forward and reverse direction for the most part. That tells us that this is an equilibrium process. What we're seeing here is not really dictated by kinetics, it's just dictated by shifting equilibrium of these reactions as we change the voltage. If instead of using polycrystalline platinum, we use single crystal surfaces, you would see that platinum 111 is essentially this broad underlying feature in this CD. Platinum 110 is the sharp feature because you would see that on a platinum 110 single crystal. And platinum 100 is this sharp feature here. So we want to use DFT to try and explain those various features, what are the processes involved, and then how are they affected by pH. And they are affected by pH, so here's the experiment. This is Uschi's group again. They change the pH, they keep us on an RHE scale so that we don't have to worry about the absolute voltage so much. And you see that the 111, the broad underlying feature here, kind of just stays where it is. But these sharp peaks, the 110 and the 100 peak, are moving all over with pH. And effectively, when you put this on the peak position versus pH on a continuous curve, what you would see is these 2 peaks shift to the right as we increase the pH. So if we can understand that, maybe we'll know something about how pH is affecting the hydrogen oxidation reaction. So to understand these peaks, we have to be able to use DFT to calculate the equilibrium constant, or the delta G, of absorbing cations and anions to and from the surface. And of course, the absorption free energy is just the free energy of products minus reactants. Products are our species adsorbed, so we can think of this again as our hydrogen on the surface. Our reactants are a surface without hydrogen on it. We may have some water there because we want to put salvation in our model in some way. Of course, an electron is a reactant. and the ion, so the proton that would be in solution. So we need to calculate the free energies of all these species, products minus reactants. The proton in solution is a little hard for us, right, with DFT, because we need to get the entropy right. This is free energy, but we can calculate proton gas pretty easily. Then we can calculate, or we can look up an experimental salvation energy, salvation free energy, and we can correct for pH. Or we can use the computational hydrogen electrode model in reference to hydrogen gas instead of proton gas. It just depends on whether or not you want to introduce essentially the experimental feature of the hydrogen equilibrium potential, or if you want to introduce an experimental salvation free energy for a proton. Either way, you get the same absorption free energy within 0.1, 0.2 volts. We then need the free energy, of course, of the proton gas.